Hello everyone, welcome to the Kinematics and Dynamics of Machinery class. In today's lecture we're going to start a new method of the kinematic analysis of mechanisms, which is the graphical solution or the graphical method. We considered the kinematics analytically using the complex algebraic method, and we said that the good thing of this method that we can using it for building MATLAB codes, for example, or any code using any programming language for building a code that would be used for making the complete kinematic analysis of the mechanism, and even tracking how the velocity and the acceleration, even the position of this mechanism is going to change over time at different configurations at different positions. This is the good thing of the complex algebraic method. And that's why it was like a fixed procedure that we stick with to, and if you apply this procedure you're going to end up with some equation that you have to solve them analytically. So this is like the analytical procedure of the kinematic analysis of the mechanisms. Today we're going to start a new method, which is the graphical method. The graphical method, we can figure out the kinematic even when we're gonna consider the kinetics of the mechanism. The good thing of the graphical method, or one of the issues of the graphical method, that we can figure out the kinematic at only one configuration, because we're already doing it graphically at a certain configuration. But if we have a code that can generate multiple configurations, so we can even use these different pegs, like you already drawing position polygon and the velocity and acceleration polygons or diagrams for a certain configuration of the mechanism, and from these graphs or these drawings you're gonna do some measurements to come up with the unknowns. As we agreed that analysis of the mechanism, it means that your objective is just to come up with the unknowns, and these unknowns we are limited for just two unknowns, whatever, for the position, velocity, or the acceleration analysis. So this method, this graphical method, you could say that this is like the experimental method, kind of finding the or studying the kinematic analysis of the mechanism. Also, we're gonna use this one for the kinetic analysis of the mechanism as well as the complex algebraic method. So through this video, I'm gonna introduce to you this method, and I'm gonna start with the position analysis, how we can do position analysis analytically. We knew how we can do it, and how we can do it graphically. We knew how we can do it analytically using the complex algebraic method. So we're gonna reconsider again many of the same problems that we did using the complex algebraic method. We're gonna repeat it again, but graphically. So for the position analysis, which is very simple actually, through the graphical method, I'm gonna explain here 4 examples which are related to the 4 cases that we cover for the position analysis. We said that for the position analysis we do have only 2 unknowns. These 2 unknowns, it would be 2 magnitudes of 2 different positions, 2 magnitudes of or one magnitude one magnitude and one direction of either the same vector or 2 different vectors, or 2 different directions of 2 different vectors. So it means that we do have 4 cases. So I'm gonna go over each one of these cases, but we're gonna reconsider it again graphically, right? So and let us start with this example one here, and let us see how we can do the position analysis, just the position analysis for now, graphically. But before I proceed, what are the 2 that you need? First of all, I advise you to have this triangular shape, or this triangle, which is known as the Aristo triangle. You're gonna find this in Galileo library, for example, or any other bookstores. You're gonna find this Aristo triangle. It has lots of lines, and even it already have embedded protractor already located or drawn here. Also there is protractor here, the angles already marked over the edges of this triangle. Like for example, if you would like to measure an angle like 10 degrees from the right, from this direction, so this is 10, 20, 30 degrees, 40 degrees, 50 degrees, is 60, and so on, keep going till the 180. If you would like to measure from the other side, so it's going to be 10, 20, 30, and keep going till the 180 on the other side. which is the same protractor already drawn here, the same angles already moving from 10 to one area or 10 to one area from in the other side. The objective of these lines is we're gonna use these lots of lines and lots of vertical and horizontal lines to draw perpendicular lines and parallel lines, and this is what we're gonna need, and especially for the velocity and the acceleration polygons, because here we are working graphically. So what does it mean graphically? It means that your calculations, all of it is going to be depending on your accurate measurements and your accurate drawing of the velocity, of the acceleration, or even the position polygons, as I'm going to show you here. That we're going to draw some things, some sketches, and from this sketch we have to do some measurements using the arrow triangle, or just to find out the angle, find out the length of a specific position vector or a specific length. So this should be the unknowns, and it means that we're gonna find these unknowns by measurements. So your drawing, it should be accurate. So if you have to draw two lines that should be completely parallel together, you have to use the arrow triangle. The conventional ruler, it won't gonna help you. This one, if you try to use a regular ruler, this won't gonna help you to draw perfectly parallel lines or perfectly perpendicular lines. You need something like this one, because we're gonna use these lines as I'm gonna show you, right? So I advise to you to have, or kind of you are required to have this triangle is known as Aristo triangle. Again, you're gonna find it in any bookstore easily. And in addition, definitely you should have pencil. You can use only one pencil is enough, and if you could bring like one pencil with 1 millimeter thickness, I mean the tip or the lead thickness, it's gonna be better. But even you can use any other like 0.5 or 0.7. But as much as you have a thicker one, it is gonna be better. It's gonna make your drawing much more clear, so you can easily measure the things here. Also for the lead grade, it is advised to have like a set that it should be like B, like this one. So for example, I do have another pencil, and this set it is already 0.7 HB. H stands for hard, B stands for like bold. It means that it can be clearly seen. And it is advised to have like B or double B even for this class, and make sure that the size of the lead set, it should be the same size as your pencil. Like this is 1 millimeter, so you should have 1 millimeter. Also, this one is gonna work for the 0.9 millimeter pencils in case that you have 0.9, so the same set is gonna work for both. But it mainly came for the 1 millimeter, and there is B, there is 2B, and so on, and there is H, and so try to skip the H, because H, it means hard lead set. It means that the pencil as you draw, it's gonna be barely seen. It will not be clear. And as you know, after you draw something and create something, and you would like to submit your homework or your work to me, you're gonna scan it. So in many of the cases, it won't gonna show up in the scan. So it is better to have a lead set that it should be like B or 2B or double B, or there are like up to 9Bs. So as much as you increase, it's gonna be better. For me, I'm using B. You can use even 2B. It's gonna be much more perfect. Okay. So this is for these two tools. In addition, definitely you should have eraser, because probably you're gonna do something wrong and you have to correct your work, so you're gonna use eraser. Definitely you need also the canvas, because we're gonna draw lots of curves and circles, and we're gonna use them for locating points, and this is because we have to do it accurately, so the canvas is a big deal for us. All right, so these are the main tools that you need for the graphical solution of the mechanisms, and this is what we're gonna do, right? But any other tool that you would like to have, it's up to you, but basically these are the fundamental things, or the main tool that we need for so far. Make sense? So how it works, let us here in the beginning, I'm just gonna focus on the position analysis. For the position analysis, as I mentioned, is to come up with some unknowns, right? So in the beginning, you're gonna work like you're already typically working analytically, like you're using the complex algebraic method. And your objective is just to find what are the unknowns, what are the givens, what are the known data, what are the missing data that you have to find, right? This is the meaning of position analysis. So almost we're gonna do the same thing that we did before. So in the beginning, as usual, what we basically do, we set up some position vectors, right? So, and I do have here, we're gonna give a name to this frame. This is the frame which is link 1, and we do have like link 2, which is the crank of this mechanism, and we do have this is the link, and this slider is already sliding over the link 04B. This is going to be the link number 3, and the slider itself is going to take number 4. So the first step is just to give number to all of these elements of the mechanism as usual. Make sense? Then the next step is just to try to set up some position vectors as usual, like you're already solving analytically. So I'm going to set up a position vector between these two fixed points, and I'm gonna give it a name like R1 vector. This position vector, it works for the frame, and in addition we do have here this position vector for the crank or the link. I'm gonna give it a name like R2 vector. In addition, definitely we're gonna have R3, as we solved this problem many times before, like we're gonna set up R3, and you should understand that R3, it works for both the slider and the link itself. In the beginning, we're gonna exclude point B because it is outside the loop, because we already, anyway, we end up with this closed loop. This is the closed loop that we're gonna consider in the beginning. Make sense? But anyway, so this is the loop that already contains 3 position vectors. So we have to identify these position vectors, which is known, which is unknown, as usual. So what we're gonna have here, your objective is just to come up with a value. You can even work on the side here and define for each one of these position vector the magnitude and the direction. What is R1 theta 1, what is R2 theta 2, and how much is R3 theta 3. Make sense? So for example, R1, it should be the 04 O2, which is already given here. R02 O4 is given by 12 inches. It means that it is already given by 12 inches. And theta 1, as usual, theta 1, if you from the start point draw a horizontal line going to the right, rotate counterclockwise, this is going to give us theta 1. Theta 1 is already given here, it should be 90 degrees. And R2, if you draw a line from the start point to the right, rotate counterclockwise, this should give us the theta 2. Theta 2 is going to be the 270 plus 15. This in total is going to give us the 295 degrees. And R2, it should be the length between O2A, which is already given, O2A given by 7 inches, so this should be 7 inches. And how about R3? R3 should be O4A, which is unknown, it is not given here, this dimension, so this one is unknown. Theta 3 should be this angle. If you draw a line from the start point, rotate counterclockwise, this should be theta 3, and here as already given, theta 3 is unknown. Simply, we didn't, nothing new. We just stick to the same procedure as we did analytical, like you're already solving so far analytical. So given this data, which case is going to be this case? This is going to be case 1. Why case 1? Because we do have 2 unknowns, and the 2 unknowns are located, or the 2 unknowns belong to the same vector. Magnitude and position of the same vector, which is R3. So it means that this should be case 1. Case 1, even in the graphical method, as it was in the analytical solution, was very simple method. It's going to be the same here for the graphical method. Your objective is just to try. I give you this drawing, I give you some data, and there are some missing data. Your objective is just to try and to graph the same shape. Then from the graph, you're going to measure and find the unknowns. And this is what we're going to do. But there is an important notice here, is the scaling. Probably for some reason, these numbers are good numbers. For example, if you just observe the smallest dimension, which is the 7 inches, and the largest dimension is 28 inches. So you have to do scaling to this dimension, because the inch, it is 1 inch, it is 25.4 millimeters. So if you multiply 7 times 25.4 millimeter, it means that you are decided to convert it to millimeter, or to scale this one as scale 1 to 1 is going to be a large dimension. So, but for the graphical things, that is fine to scale. So the first thing that you're going to do here, after you identify the unknown and the givens and know exactly what you are seeking graphically, and identify the case, your objective directly is to work on the scale. So for the scale here, your objective is just to observe the small number and the largest number, right? So the small number is 7 millimeter. For example, if I decided to draw a line with 7 millimeter, it's gonna be very short. But if you agree with the 7 millimeter and use this one, that is fine. It's up to you. So the key idea what I mentioned here is just try to scale up or scale down the dimensions to be consistent, and you can clearly do your measurements. So for example, I'm going to assume that this smaller number, which is the RA2, it should be AO2, it should be R2. So I'm going to assume that the R2, which is already given by 7 inches, I'm going to assume that this 7 inches, I'm going to do this one as 30 millimeter. So this is the real or the exact value, but this is the drawing scaled value. Make sense? And so how about if this is the 7 millimeter, it should be 30, what should be the 12 and the 24 and the 28? So the 12 inches, it should be something, and the 28 inches, it should be something as well. So what is this something? You're just gonna do cross multiplication. For example, this value should be the multiplication of the 30 times the 12 divided by the 7. So this value here, it will be 30 times 12 divided by 7 equals, if you did the calculations, this is gonna give us 30 times 12 divided by 7. This is gonna give us at the end 51.43, for example, millimeter. So what does it mean? It means that when you decide to draw 12 inches, the 12 inches dimension should be drawn as 51.43. How about the 28? Do the same. The 28 is going to be the multiplication of the 30 times the 28 divided by the 7. This is how it works. So it's going to be simply, it's going to be the 28 times the 30 divided by the 7 equals, if we did the multiplication, this is going to give us the 120 millimeter. Alright, so I've done the scale. Your objective now is just to draw. So let us use this area for the drawing. When we're gonna consider the complete, now we're just working on the position analysis, so there is no need to use a different sheet or a separate sheet for the drawing. But basically this is what we're gonna do when we consider the complete kinematic analysis. So what does it mean? It means that you have to have all of the drawing, all of the position, the velocity and the acceleration polygons or diagrams should be drawn over one sheet, because you're gonna use them. For example, once you finish the position analysis, you're gonna use the drawing for the position analysis for the velocity and then for the acceleration. Okay, so all of them, they should be over the same sheet. But since here I'm just focused on the position analysis, so I'm gonna use the same sheet that I'm typing in for the graphical things. So in the beginning, your objective is just to draw the lines that already, or the position vector that completely known. We start by drawing the position vector that completely known. We do have here 3 position vectors. We have R1 is fully defined, and R2 is also fully defined, but R3 is completely unknown. So it means that I'm just gonna keep the R3 till the end, which is the unknown. So I'm gonna start with R1 and R2. You can start with either R1, R2, it's up to you. R1 is already vertical and it should be set up between 2 points. So if we consider that this is our start point, which it should be like 0.04. So I'm gonna start from any point to be 0.04, and then your objective is just to draw a completely vertical line. How can I know that this is a completely vertical line? It is at first to have this line vertical and to be parallel to the edge of your drawing sheet. So this is the drawing sheet here, and there is multiple lines here, right? So try to align one of these lines to the edge of the drawing sheet as already given here. Just align this black line of the triangle to the edge of the drawing sheet and just mark a point to be your start point, right? So for example, I'm gonna start from this point and I'm gonna align this line to the edge. Then I'm gonna draw a very light vertical line in the beginning, just any line that is vertical. Then your objective is to measure over this line, this vertical distance, the distance O2, O4, which it should be R1. R1 is already 12, but after the scale, the 12 became 51.42. So what I'm going to do, I'm just going to measure over this vertical line. In the beginning, draw a very light line that is barely seen. Then measure over this one, 51.43. 51, so it's going to be 10, 20, 30, 40, 50, 1 point something. So just 50, just mark a point after the 51, right? Like a point between the 51 millimeter and the 52 millimeter. Mark a point. This point definitely should give us the other point, which is the 0.02. Make sense? So now we set up here, we can even mark hard or draw hard over this line. This is gonna give us the first position vector, which it should be the R1. So we got the R1 vector. Very simple. Make sense? And these are 2 points that we located here in the drawing to draw the other position vectors. Now if we move to the position vector R2, it should be set up between O2 and another point A. We don't have point A here, but we do have point O2. So what does it mean? From point O2, your objective is just to draw this line. But this line, it has an angle. Any position vector, you have to define the angle first. So that's why this one was very simple, because it is, anyway, it is vertical. It has 90-degree angle. But this one, it has an angle of 295 degrees. But it is not necessary to measure all of this angle. You can just simply measure the 15 degrees that already given here. So what does it mean? I'm gonna measure using the canvas, the protractor. I'm just gonna fix here at this point, right? And I'm gonna use the protractor to measure 15 degrees from this vertical side. It means that this angle, it should be 15 degrees as already given there, right? So if this is 15, it means that I have to move from this point. I have to move here. I have to measure like 10 degrees, then 5 degrees, and mark a point. That is fine if it is over the disk. Your objective is just to mark the point and fix the paper and connect this point to this point just to find the angle, right? So simply, now I got this angle is completely 15 degrees. The other option is just to measure the other angle. This one, it should be the 75 degrees. So what does it mean? You can do the same, and instead of measuring 15 degrees from this side, you're gonna measure the 75 degrees from this side. So it's gonna be like 10 degrees, 20, 30, 40, 50, 60, 70, 75. You're gonna end up to the same point, and then connect the point to this point. You're gonna end up with the locus, where it should be. This is the direction of the position vector R2. Now the length of this position vector R2 is already given 7 inches, and we agreed that we're gonna draw the 7 inches by 30 millimeters. So what does it mean? Your objective is just to measure 30 millimeters, which it should be 3 centimeters over this line, and mark a point. So this point, and if you go over the line one more time to make it clear, this point definitely should be point A. And this position vector, it should be the position vector R2 vector as we already got it. Make sense? So we draw R1, we draw the R2, and we get point A. Now we have to set up R3. R3, it is very simple. We got it. We got R3 very simple. Why? Because R3 should be set up between O4, which is this point, and A, which is this point. So we do have everything. So simply, if you connected these 2 points together, we're gonna end up with R3 vector. We're gonna end up with R3 vector that we already set up there. R3 vector as follows. So this drawing here is known as the position. This is known as the position polygon of this problem or this example. This is known as the position vector polygon. It's just your objective to draw this thing. For example, for this problem, for some reason, you may be required to find the displacement of point B, right? The absolute displacement or the absolute position of point B with respect to another point like point O or point O2 or O4. So to find all the data regarding point B, we have to locate point B over the position polygon as well. As we did for all the points O2, O4, and A, we still need to add point B. Point B is very simple point because the position or the distance between O4B, the distance between O4B is already given by 28 inches, right? So the 28 inches, according to the new scale, I should draw this one as 120 millimeter. So I'm gonna measure over O4, from O4, I'm gonna measure 120 millimeter, which it should be 12 centimeter. So you just gonna measure 12 centimeter, which it should be a point up there, and connect these lines or these points together. We're gonna end up this point here up there, it should be the point B. So this is the complete position polygon for this mechanism, including it also the exact location of point B, right? So did we finish the position analysis? Not yet. Your objective after you do the measurement, the drawing, you have to measure. You have to come up, find the unknowns. To finish the position analysis is to find the unknown. The unknowns here are R3 and theta 3. So how much is R3? R3 should be the distance between O4 and A. And we already got it. So we got it graphically. So your objective is just to measure the distance between O4 and A, as already given here. Make sense? Then if I measure this dimension, this distance, I'm getting it like nearly 25 millimeter. This is what I'm got. So what you're gonna do after you finish, you're just gonna work over the graph. So you're gonna say that from the position polygon, we're gonna do some measurements. From the position polygon, I got R3. This is the unknown R3, which it should be the distance from O4 to A. I measured this distance. I got it by 25 millimeter. This is from my graph. But the exact value should be in inches, right? Because we did scaling, so I have to scale back. So I did scale, I have to scale back again. How we can scale back? Your objective, if you can observe any one of these numbers, when we did calculation, we multiplied 30 times 12 divided by 5. So we're gonna do the opposite. We're gonna multiply divided by 7. So we're gonna do the opposite by multiply times 7 and dividing by 12. Like for example, I already got here, this is the scaling, right? So I was using 7 inches and I converted the 7 inches, drew the 7 inches as 30 millimeter. So what I'm gonna do, I'm just gonna I got from the graph, this is the graph, right? This is the drawing. I got from the drawing 25 millimeter, how much it should be in reality, the real dimension, how much it should be. So this should be the R3 that I'm seeking. So if you did here scaling, so your objective is just to do the multiplication in this way. 7 times the 25 divided by the 30. You're just gonna do the opposite. Instead of multiplying 30 times the dimension over 7, you're gonna multiply times 7 and divide by the 30, the opposite. So this is gonna be here, I'm gonna end up that the exact value of R3, it should be the 25 times 7 divided by the 30, which is gonna be in terms of inches, 25 times 7 over 30. This should be less than 5.8 inches. So this is the R3 value. Make sense? What is the other thing that is missing is the angle theta 3, right? So theta 3, it should be this angle as we defined it here, right? The angle between the horizontal line going to the line here. So what does it mean? It means that if we do a horizontal line, if we do have a horizontal line here, just make that this black line of the triangle already aligned with the vertical line that we draw in the beginning, and draw a horizontal line. Then over this line, you just gonna, from this point, your objective is just to measure an angle which is theta 3. Theta 3, it should be just measure the angle. We are not drawing an angle, we just measuring the angle. So theta 3, do you see this line here? This long line, right? As you can see, this line is gonna go, it's gonna be like, you're gonna observe the line much more better from up there. So the angle here, it is 10, 20, 30, 40, 50, and you're gonna find like it is 55, 56, and it is like in between 55, 56, 57, kind of. It is 57.1, for example. So for example, if you said that it is 57, that is fine. It means that we're gonna say that theta 3 is gonna be 57 degrees. This should be this angle, which it should be the theta 3, which is this angle from the measurement. The question is, should I do any scaling to the angle? No, the angles are not scaled. The angle, if it is given, If it is unknown, you just measure or use the angle as it is. There is no scaling for the angle. The angles cannot be scaled because the angle is dimensionless. But we scale something that has a dimension or have a unit, like the R or the which is basically for this case is gonna be the for the position analysis is gonna be the magnitude only, but the angles there is no scaling for the angle. So these are the dimensions or the unknowns, and by finding these unknowns we already done and finished the position analysis of this mechanism graphically. If you compare these two values to the analytical solution of this problem, you're gonna find this one in lecture note number 2, the same example. If you compare the two numbers, you're gonna find that they are very close, but definitely it is hard to find the analytical or the graphical solution exactly the same like the analytical solution, unless you are using a very accurate software like AutoCAD for drawing or SolidWorks. But here, since we are doing by hand, so there's definitely some error or some deviation from the analytical solution. So that's why, but it is very close. If you compare the two numbers, you're gonna find that they are very close to each other. So this means that we are in a good shape and this problem or this example is perfect. So this is for the first example. Again, this is related to case 1. We're gonna repeat for the other cases and moving to the second case through this another example here, which is example 2. We're gonna do the same, stick to the procedure. The first step is just give numbers to the different elements. We do have the frame, which is the ground. In addition, we do have link 2, which is AB, which is the crank, and link 3, which is PC, in addition to the slider 4, element 4. Then your objective is just to set up position vectors between all of these different elements. So we do have the first position vector, which should be like R1, or you can give it a name like R4, because this R1 you should understand that it is mainly made for the slider. This is where the slider is going to move, so it is better to give it a number like R4, where 4 refers to the slider number 4. And R2, which is the position vector for the link that rotates. This link AB gives rotation as R2 vector. And R3, this is for a connecting link. This link is just doing general plane motion, which is R3 vector. Make sense? So we have here 3 position vectors, and there are some given data and definitely there are some unknowns. So let us figure out what is given, which is unknown. And we have to define R2 and theta 2, we have to define R3 and theta 3, and we have to define R4 and theta 4. There is no R1 here because I didn't use R1. So R2, it should be the distance between AB, right? AB is already given by 50 millimeters, so R2 is already given by 50 millimeter. Theta 2, it should be the 45 degree, because if you draw a line from the start, rotate counterclockwise, this is gonna give us 45 degrees. R3, it should be the distance between B and C, which is not given here, so it is unknown. Theta 3, it should be the angle. If you draw a horizontal line going to the right and rotate counterclockwise, this should give us this angle here. So it means that for now our theta 3 is unknown. Remember that we agreed that we are not going to do any calculation of the trigonometric calculation in the beginning unless you have the number of unknowns is higher than 2. We are just limited for just 2 unknowns. R4 should be the distance between A and C. The distance between A and C also is unknown, so this is the third unknown. And the angle of our theta 4, it should be 0 because it is already going horizontal. Make sense? So we end up with 3 unknowns. It means that we have to do calculation to come up with one of these unknowns, like theta 3, for example. We can find theta 3 from the graph. If you sum, as you know, the sum of these 3 angles, it should be 180. So this angle here, between these two R2 and R3, it should be the 45 plus the 60, subtracted from the 180. This should give us 75 degrees, this angle. So this angle is 75 degrees. You can use this angle, or simply you're gonna find that this small angle here is 60 degrees, which is the same angle like this one, right? So the theta 3 should be the 360. It should be theta 3 equal the 360 degrees negative 60 degrees, which is gonna give us 300 degrees. So it means that theta 3 is gonna be 300 degrees as already given here. So as you can see, we do have only two unknowns. These two unknowns are two positions for two magnitudes for two different positions, R3 and R4. So what does it mean? It means that this should be case 2 according to the different cases that we defined before for the analytical solution. We still sticking to the same 4 cases. So this should be case 2 since we do have two different magnitudes of two different positions. And then your objective is just to do scaling. What comes next is just do scaling to all the dimensions. So the only dimension that we have here is the R2. This is the only given dimension. So what does it mean? It means that I'm going to do scaling for the R2, which is the 50 millimeter. I can draw the 50 millimeter at just 50 millimeter. So I don't do scaling. It means that you are using 120 scale. But if you would like to change this number, it's up to you. This is all the time. Keep the rail on the left and the drawing on the right in this way. So what does it mean? The 50 millimeter would be drawn 50 millimeter as it is, because the 50 is not a big deal. We can, it will be confined here some or located here. We can manage drawing 50 millimeter within this area, no problem. Make sense? So this is for the scaling. Then the next objective is just to start drawing as we did before, creating the position polygon for this graph. So as usual, we're gonna start from any point, and we're gonna start by drawing the lines or the curves that already, or the position vector that already completely given. The one that is completely given is only one position vector, which is R2, right? R2 and theta 2 were already given. So I'm gonna start from any point. Let us assume that this is point A. I'm gonna start from any point, assuming that this is point A, the start point. And your objective is just to draw R2. To draw R2, you have to measure the angle first. Then you're gonna draw a line, and then over this line, you're gonna measure the distance AB, which is already given by 50 millimeter. So from this point, I'd like to measure an angle of 45 degrees. Remember that this Ariosto triangle itself, this triangle by itself, it has this angle is 45 degree, this angle is 45 degree, this angle is 90 degree. This is known as, this is like the conventional 45 degree triangular shape. So what does it mean? I can measure the angle directly by drawing the edge. For example, make sure that this solid edge here, this solid edge, it is considered to the, this solid line is considered to the edge of this drawing sheet. Then draw a line. This line automatically has an angle over the horizontal axis by 45 degrees. Then I'm gonna mark the point A over this line directly. Like this is, assume that this is point A. Make sense? So even if you try, and if you draw here a horizontal line, again, align this solid line to the edge of the drawing sheet and draw a horizontal line. This line, the angle between this line and this line, definitely it is 45 degree. If you try to double check, it will be completely 45 degree. Again, why? Because this triangle is already 45 degrees. This is 30, 40, 45 degrees, right? So it is completely aligned here. Make sense? So anyway, we got this angle with respect to the R4, and your objective is just to measure the distance AB, which is already given by 50, and you decided to draw the 50, just 50, the same. It means that I'm just gonna measure here 50 millimeter over this line, 50 millimeter, 10, 20, 30, 40, 50, and mark a point. This point definitely should be point B. And just go over this line to make it clear. And this definitely should give us the position vector R2. So we got 2 points so far, which are point A and point B. Now we have to look at point C. But point C, we cannot locate this point since R4 is not known. The distance over the horizontal axis, it is not given. Also, this distance is not given. So for the case, in case that the two position or two magnitudes of two different positions are unknowns, we have no ability except we draw out two lines with the angle. We're gonna use the angles just to draw two lines. Each one of this line is known as engineering locus. What does it mean, engineering locus? It means that the point that you are seeking, it should be located over this line. So start, for example, with theta 4. We already have theta 4 equals 0. So what does it mean? It means that in theta 4, to locate point C, according to R4, it should be over the horizontal axis, the same horizontal axis, but somewhere over this horizontal line. So what I'm going to do from point A you have no ability except to draw a line that is just horizontal. So what does it mean? It means that point C, it should be located over this horizontal line somewhere. But where exactly, we have no clue. It means that you just use the angle, theta 4. So I draw a horizontal line and that's it. Point C should be somewhere here or there or there or there. We don't know yet. So this is the first locus. This is locus 1 to point C. This is locus 1 to point C. This is the first locus for point C. Locus, it means that point C, it should be located over this line, but somewhere we have no clue. Make sense? We need another locus, because from the other locus, when it intersects with the first locus, the point of intersection definitely it would be point B. So we need another locus or a second locus, which should be through the R3, because we already finished R2 and we finished the R4. We have no other thing that we can do for R4 except the angle. How about R3? In case that the vector, it has only direction, you just gonna draw a line with this angle with any length. But how much is the length of this line? We have no clue, because R3 is unknown, right? So now we're already working over R3. R3 should be generated between point B, and we already have point B here, and point C, but we don't know where is point C. So from point B, you're gonna measure the angle here to draw a line. This line is at angle 60 degrees. It shouldn't be, it is not necessary when you do graphing or work graphically, it is not necessary to use the 300 degrees. So simply you're gonna draw 60 degrees from this point. You're gonna measure 60 degrees this direction from this point. So you're gonna, from this point, make sure that you do have the triangle is already perfectly aligned to the edges of the drawing sheet, to have it like horizontal and vertical. And then your objective is just to measure 60 degrees. So this is 10, 20, 30, 40, 50, 60 is gonna be a point here. Then from this point, just keep the paper as it is and connect these 2 points together. Just draw a line in this way. This line, it should be another locus. This line is at an angle. I measure this angle to be 60 degrees. So this line, it should be a second locus. This is locus 2 for point C. So I do have one locus for point C. It means that point C somewhere, it should be located over this line somewhere. This is another locus for the same point, that it should be located over this line, but somewhere. The point of intersection definitely is going to give us the point C that we are seeking. Very simple. Make sense? So this definitely, the intersection point of the two loci, this known as the point, this is going to give us the point that we are seeking, which is point C. Then simply, if you just go over this line one more time to make it clear, and the other line to make it clear, we already end up with these R4 and R3. We got here this one. This one definitely, it should be the R4 vector, typically the same like the given mechanism, and this should be the R3 vector, typically the same as the given mechanism. Make sense? So we have done, we finished. We draw the mechanism to the scale as already given there, but there are some unknowns. So from the position polygon, we have to do some calculate or measurements to be accurate, not calculation, to do some measurements to come up with the unknowns. The unknowns here are R3, which it should be the R3 length, which is the distance between B and C, which is the distance between B and C as already given there. So your objective is just to measure this distance. So this distance from the measurement, we're gonna get it by nearly like 41 millimeter, right? So I got R3 from the position polygon by 41 millimeter, right? How about R4? It should be from R4, it should be the distance between A and C, and the distance between A and C, which is already given here. If you measure this one, 10, 20, 30, 40, 50, and you do have like 56 millimeter kind of. It is not necessary to find it exactly as much as you're gonna close to the analytical solution, so that is fine. It is totally acceptable. So we do have R4, we got R4 and R3, and these are the unknowns. Do I have to do scaling back to this one? Yes, but the scaling back here, it is not necessary since we're already using the semi-scale. The 50 should be 50, so the 41 it should be 41 as well. 56 it should be 56. It means that we didn't do change in the given dimensions. It means that that is fine to use the same scale. Okay, so the key idea, my advice is, if you do your best to use scale 1:1 to save time. So I won't gonna spend time to doing reverse of the scaling that I've did here, that I've done here since I'm using 120 scale. So it means that any measurements that you're gonna do for the magnitudes will be definitely the same. So we find the unknown. It means that we already finished the position analysis for this mechanism. This is in case that it is case 2. So for case 2, you're gonna find two magnitudes unknowns. You have no ability except to draw a line, two lines for the two unknowns positions, and they gonna intersect together at the point of intersection. Like this is R4 is unknown, R3 is unknown. Both they gonna intersect and meet together at point C. So you're gonna draw one line, another line, point of intersection is gonna be point C, and do the measurements. Make sense? This is for the second case. For the third case, or the third example here, we already given this mechanism, and let us do the same. This should be element 1, this should be element 2, element 3 which is the link, and element 4 which is the slider. Make sense? So then we're gonna set up some position vector. I'm gonna assume that this is R2 vector, and this is gonna be R3 vector as usual. And we're gonna set up here R4. It's typically the same like the previous example, right? This is R4 vector, where R4 is gonna work for the slider, right? Then your objective is just to find the givens and the unknowns. So what should be R1, what should be theta 1? Oh, there is no one actually, there is theta 2 and R2. How much is R3 and theta 3? How much is R4 and theta 4? Right? R2, it should be AB, and AB is already given by 50 millimeters, so it is already given 50 millimeter. Theta 2, it should be the 60 degrees, right? It is already given. But R3 BC, which is already RBC, is already given by 150 millimeter. It is already given. But theta 3, we have no clue how much is theta 3, right? So theta 3 is unknown. How about R4? R4 should be the distance AC, and it is not given with the distances, so it means that it is unknown. This is the second unknown, and theta 4, it is definitely 0 degrees. So it means that we're going to end up with just two unknowns, which are the theta and magnitude, the direction and magnitude of two different vectors. This is case 3. So this indicates that we're already working over case number 3. Then what we're going to do, we're just going to do scaling, the scale. These are the two dimensions, 50 and 150. If you decided to use them, 50 and 150, that is fine. If you're going to find, for example, the 150 millimeter, which it should be 15 centimeter, it is too big over the area that you're using for drawing, you have to scale down, right? But for me, that is fine to use 50 and 150 millimeters. So I'm going to keep the scale as 1:1. It means that I won't going to change the dimension to save time. But if you had to do scaling, either up or down. For example, if these numbers are too small or these numbers are too huge to be confined within this area, so you have to do scaling up or scaling down, depends. So now I'm gonna move directly to the drawing, and I'm gonna start with the given position. The completely given position vector is the R2. So I'm gonna start with R2, starting from point A. So I'm gonna make a point. You can easily, for example, just draw a horizontal line in general to be your reference for any horizontal line, and from any point you're gonna draw a vertical line to be your reference for any vertical line, and make sure that these lines to be parallel to the edges of the drawing sheet. So these two lines, this is my reference for any horizontal line, my reference for any vertical line. Then I'm gonna start from a point like this one, assume that this is point A. In this case, then to draw the position vector, for any position vector that is completely defined, you have to measure the angle first, then draw the line, conventional. So I'm gonna measure the angle first. I'm gonna stick to this point here, measure the angle which is 60 degrees, so 10, 20, 30, 40, 50, 60, and mark a point. Then from this point, you're just gonna draw a line in this way. So this line, it should be locus to point B. What does it mean, locus again? It means that point B should be located somewhere over this line. But where exactly, it depends on the distance between A and B, which is already given by 50 millimeter. So what does it mean? You're just gonna measure 50 millimeter over this line and mark a point. This is gonna give us point B. And then your objective is just to go over this line one more time so you can see the vector, the position vector, and mark that this is position vector R2. Very simple. So we got 2 points so far. We are seeking a third point, which is point C. This is the last point that we need, right? But for point C, there is a problem. This is a different case. The previous case, theta 3, theta 4 were given. So we measured the angles and we drew two loci, two lines, and these two lines intersected together at point C. But here it is a different case. Here we do have one position vector, its direction is known, and the other position vector, its magnitude is known and the direction is unknown. So the first case, in case that you do have a position vector that is fully defined, we measure the angle first, draw a line, then measure the length over this line, as we did for the position vector R2. But in case that you do have a position vector with a given direction and known magnitude, you're just gonna draw a horizontal line, or you're gonna draw a line with this angle. You're just gonna measure the angle and draw a line, and that's it. So again, for the position that is fully defined, that is completely defined, we are doing 3 steps. Measure the angle first from any one of the 2 points, because this one is set up between A and B. If you do have A, you're gonna start drawing from measuring the angle from A. If you do have B in the graph, this is the position polygon, you're gonna start from point B. Whatever the point that you already have for this mechanism, for this completely defined vector, you're gonna measure the angle. 3 steps. Measure the angle first, then draw a very light line that is barely seen. Then over this line, you're gonna measure the distance between the 2 points, or the length of the magnitude R of the position vector. So measure the angle, draw a light line that is barely seen, and then measure the length over this line and mark the other point and connect them. This is in case that the position is fully defined. How about if it has some of the unknowns? So one of these steps will be missing, right? So let us work over this position vector 4. Position vector 4, the direction is known, so I can measure the angle. Then I can draw the line, which is barely seen line, the light line, but I cannot measure the length. I have no clue how much is R4. So I'm gonna do the first 2 steps and I'm gonna skip the third step. And this is what I'm gonna do for position vector 4. So position vector 4, its angle is theta 4, it is 0, and this means that this position vector is horizontal, and this is already horizontal in the drawing here. So what does it mean? It means that, and it should be set up between point A and point C. I don't have point C, but I do have point A. So from point A, I'm gonna draw a line that is horizontal. This line, it should be locus to point C. Make sense? So I got the first locus here. So again, there are 3 steps. Measure the angle is 0, it means that it should be horizontal line. Then from any one of the 2 points that belong to the position vector, I have point O, draw a very light line. So I've done the first 2 steps, but I cannot move to the third step, that I can't measure over this lines anything because R4 is unknown. Make sense? And this is gonna give us the first locus. So we have done of this position vector, we have done of this one. How about the third one? The R3. The R3, it has a magnitude, but the direction is unknown. So if we decided to stick to the 3 steps, I won't gonna able to measure an angle because the angle is unknown. Hence, I won't gonna be able, since we cannot measure the angle, we cannot draw the line, the light line. But we do have the length. We do have only one information, only data that we have. In this case, in case that you do have a position vector with unknown direction, this is what you're gonna do all the time. So you can divide it, and even in lecture 5, in lecture note number 5, that I'm gonna scan it and give it to you, you're gonna find that I already discussing all of these different cases. In case that you have the position vector is fully defined, you're gonna measure the angle, draw a light line, measure the length. It is very simple, 3 steps. In case that the position vector has a known magnitude, your objective is just to measure the angle, draw a light line, but you cannot measure anything. So that's it, 2 steps only. For the position vector with unknown direction, the direction is not given, it is only 1 step that you're gonna do. And for this position vector, you have to use the compass. All the time you have to use the compass for the position vector that is already with unknown direction. So R3, the length R3 is 150 millimeter. So your objective is just to measure 150 millimeter using the compass, right? So if I try to measure the 150 millimeter with the compass, I won't gonna able to open it, right? It is not, it cannot be open to the 150 millimeter, right? So I do have up to 140. For this case, it means that you have to do scale down. It means that the 150, I won't gonna able to use it. So I have to do scale down. You got my point? So for this case, I'm gonna go back here, do scale down to these dimensions. So I'm gonna work on the scale here. So the 50 and the 150, it won't gonna work. That is fine, for example, to use the big issue with the 150. So let us scale it down somehow, and I'm gonna assume that the 50 millimeter, I'm gonna draw this one like 30 millimeter. So what should be the 150 millimeter then? If you did the calculation, multiply 30 times 150 divided by 50. So 150 times 30 divided by 50, this is gonna give us 90 millimeter, and definitely I can measure 90 millimeter over the curve. So what I'm gonna do, I'm gonna shorten somehow this length, right? So I'm gonna remove this point and shorten, move it back. Here should be over the same line. This distance, it should be the 30 millimeter. So the point, it should be here. It means that this should be point B. Then I'm gonna remove the extra things here for this position vector. So this should be point B, and this should be position vector R2. Make sense? So I changed the scale. I had to, because the compass it won't gonna be open with the 150. Now I can open the compass with the 90. This is the 150, should be 90 in the drawing. So I can measure 90 millimeter here using the compass. So again, for the position vector with unknown direction, you have to use the compass for this position vector. You're gonna open the compass with the magnitude of this position vector, which is 150, which after the scale the 150 became 90. Then this position vector, it should be set up between 2 points, which is here I'm talking about R3. It should be set up between either point B or point C. In the graph here, I already have point B, but I have no clue where is point C. So from point B, you're gonna fix with the metal tip and draw an arc. Very simple. This arc, it should be locus to point C. This is the second locus for point C. So now I do have 2 loci, which is this horizontal axis or this horizontal line, and this curve is another locus. Their intersection point, it should be definitely point C that we are seeking. So this is gonna give us point C. Then your objective is just to connect these points. If we connected the C to B, this should give us the position vector R3, right? This should be the R3 vector as already given in the drawing. And this horizontal distance or this horizontal line, it should give us the R4, which is the position vector for the slider, which is R4 as already given here. So this is what I've drawn here. This is the position polygon that I'm talking about. Position polygon. But we didn't finish the position analysis yet. We have to come up with the unknowns, right? So from the position polygon, what we're gonna get here, we're gonna get these unknowns. The unknowns are 2 things, R4 and theta 4, right? But remember that R4, it will be scaled. We're gonna do some scaling to the R4. Make sense? So what I'm gonna do here for the R4, your objective is just to measure the distance AC, because R4, it should be the AC distance. Measure this distance. We got it by, let's say, like 10 centimeter and 1.1, which it should be 101 millimeter. So we got it from the measurement by 101 millimeter, but this one, it should be scaled back. So this is the drawing. Remember that this is the side of the drawing and this is the real dimension. So if the 101 is represented here, I got 101 millimeter. How much it should be in reality? So do the scaling. So you're gonna do the multiplication of 101 times 50 divided by 30. Do the opposite to the thing that you did for the calculation of the 90. So it means that the R4, the exact value of R4 after scaling, it should be the 101 millimeter times 50 divided by 30. This should give us the R101 times 50 divided by 30. This is gonna give us the 168.34 millimeter. This is the exact value or the real value for the R4. How about theta 3? Theta 3, your objective is just to measure the angle, and as we agreed, the angle, the angle itself, it has no scaling, right? So theta 3 should be this angle. But how about if I measure this angle? That is fine, then you can subtract from the 360 degrees. So what I'm gonna do, this angle, it should be set up between the horizontal line from point B to this R3. So what I'm gonna do from this point B, I'm gonna draw a horizontal line, but make sure that this line, it should be horizontal. So that's why you have to use the line that you created in the beginning for the horizontal and vertical line for the parallel and the perpendicular lines. So I'm gonna draw this horizontal line, then from this line I'm gonna use the protractor over the triangle to measure this angle. This angle, as you can see, this is the line that I'm talking about, right? And this is the horizontal line, so I need this angle here. This angle, it will be, if you just measure, it will be 20, and it is between, the line it is located between the 21 and the 22. So that is fine to say that it is 21.5 millimeter. So theta 3, it will be 21.5 degrees, I'm sorry. So this is gonna give us the angle theta 3, which it should be this angle, by the way. It means and this is what I mean, that this angle is 21.5 degrees, but the angle, it should be negative since we're already moving in the clockwise direction. This angle, it is 21.5 degrees. But if you need it positive, so theta 3 should be subtracted. 360 negative the 21.5 degrees. This is gonna give us the angle in terms in the positive in case that it rotates in the counterclockwise direction. 360 negative 21.5 give 338.5 degrees. Make sense? So again, in case that you have a position vector with unknown direction, you have to use the cams for this position vector. Make sense? So this is, for example, 4, which is for case 3. Now we're gonna move to case 4 through this example number 4 here. So this is a 4-bar linkage. We do have the link O2A. We're gonna give a number to the frame again. And we do have, this is the crank, which is O2A, and we do have a connecting link, which is AB, in addition to another link, which is O4B, right? This is a 4-bar linkage. There is no sliders here. Then your objective is just to set up position vectors as usual. So we're gonna have here, this is like R1, this is works for the frame that is fixed, that is not rotating, is not increasing length or decreasing length. And we do have the crank, which is link number 2, this is R2 vector, and we do have the connecting link AB, which is doing general plane motion as R3 and the R4. Also doing, this one is doing rotation about 0.04, simply, right? So this is R4 vector. Then your objective is just to define which one is given, which one is unknown. What are the given there and unknown there for this mechanism? So what we're gonna do here for this one, on the side here, we do have R1, we do have theta 1, we do have R2, theta 2, R3, and theta 3, R4, and theta 4. Make sense? So if I ask you how much is R1, it should be the distance between O2, O4. O2, O4 is already given by 50 millimeter, right? It is already given here. So this should be 50 millimeters. And theta 1 definitely should be 0 because this is it is a horizontal position vector. How about R2? R2 should be O2A, and O2A is already given by 30 millimeter. How about theta 2? Theta 2 should be the angle 120, because if you draw a line horizontal, going to the right, rotate counterclockwise till you hit the R2, this is going to give us the 120 degrees. So it is already given. How about R3? R3 should be AB distance. AB distance, RAB is already given by 100 millimeter. Make sense? But how about theta 3? It is not given, right? This should be theta 3. We have no clue how much is this angle, so it is unknown. How about R4? R4 it should be O4B. O4B it is already given by 70 millimeter, so it is 70 millimeter. And theta 4 it should be the angle. If you draw a horizontal line going to the right, rotate counterclockwise, this should be theta 4. So again, theta 4 is unknown. And that's why we do have here two unknowns, and that's why this is case 4. As we agreed, case 4, it means that we do have two directions of two different position vectors are unknowns. And this is case 4, that basically it was taking time and had lots of calculations in the analytical method. Here we're gonna find that it is much more easy if we can use the graphical method to find these two directions. Make sense? Now we're gonna do as usual, we're gonna move to the drawing, but we have to do scaling, or we have to see if we decided which scale, if we decided to use scale 1:1 or change the scale. So if you're gonna just observe the numbers here, we do have 30, which is the smallest dimension, and the largest dimension is a 100 millimeter. So you have to double check that your canvas can be open with 100 millimeter, which is the largest dimension, and it can be open more than 100 millimeter. Also the 30 millimeter, which is the smallest dimension, and 30 millimeter is quite good. So you can see the dimension, you can see the line. So what does it mean? It means that for this example, that is fine to work with the scale. The scale that I'm gonna use for this case, I'm gonna use a scale 1:1. Make sense? So I won't gonna change the dimension, I'm gonna go directly to the drawing. Again, just draw a vertical line. Make sure that this vertical line, make sure that it is better to have this vertical line. You can draw any vertical and horizontal line to be your reference, but it is better to have this vertical line better to the vertical edge, because probably you would need the edge for drawing lines, other lines. So I'm gonna draw this vertical line, parallel to the vertical edge, and I'm gonna draw this horizontal line parallel to the horizontal edge. Make sense? So I got these two lines. These are my main reference in addition to the edges of the drawing sheets, since they already parallel to the edges, right? Then again, start with the position vectors that are completely defined. We do have here two position vectors fully defined, which are R1 and R2. So I'm gonna start with these two position vectors. You can start with either R1, R2, it's up to you. If we started with R1, which is the much more easy, again, it is 3 steps. Step 1, draw the angle. Step 2, draw the light line. Then over this line, I'm gonna measure the 50 millimeter, right? And this R1, it should be set up between O2 and O4, but we don't have any points here, so it's up to you. I'm gonna locate point O2 first at any location. Let us assume that I'm going to locate point O2 here. This is point O2. Then I'm gonna draw a line horizontal, because it is horizontal. It means that looks like you already measured. This is like you already measured the angle. Theta 1 is 0 degree. So I draw a horizontal line, then very light line. So this is like step, this is O2. Then I measure the angle, then I draw the line. This is the first 2 steps. Then the third step is just to measure the distance, which is 50 millimeter. So from the O2, I'm gonna measure 50 millimeter here. If you measure 50 millimeter, this is gonna give us a point. This point, it should be the O4 point. Make sense? So I got this should be the first position vector, which is R1. Very simple, you can draw this one. This should be R1 vector. Make sense? So we got R1. How about R2? R2, again, it should be set up between either point O2 or A. We don't have point A here, but we do have point O2. So I'm gonna start from O2, and it is fully defined. It means that I can apply the 3 steps: measure the angle, draw a light line, measure the magnitude over the line. The angle is 120 degrees. It should be rotating in this direction. So from point O2, I'm gonna measure 120 degrees, right? So 120 degrees, it should be, this is up to here. This is 90 degrees, then this is 100, 120, then 110 and 120. and then mark a point. That is fine if it is over the disk. Don't move the paper and or the drawing sheet and connect this point to this point, right? You're gonna end up with like this is the 120 degrees. This angle, it should be the 120 degrees that I'm talking about. Anyway, from O to A, the distance it should be 30, which is R2. R2 is already given by 30 millimeter. So I'm gonna measure 30 millimeters since I'm using scale 1 to 1. So measure here 10, 20, 30 and mark a point. So this point definitely should be point A. Then you're gonna go over this one more time for the position vector 2. So for position vector 2, I have applied the 3 steps. I measure the angle, draw a light line, then I measure to draw the position vector. So I've done of the fully completely defined position vector. Now I'm gonna move to 2 unknown or 2 position vectors that include unknown, and these unknowns are directions. We said that for a position vector with a known direction, you have to use the comps for this one. But if the magnitude is the unknown, you're gonna draw a line that's it. You're gonna measure, you're gonna apply the first 2 steps. In case that the magnitude is the unknown, but here the direction is unknown, it means that the first step I won't gonna able to apply this one because the direction is unknown. So then also I won't gonna able to draw the line. The only thing that I can have is only one step is just to identify the distance, which is, or the length, which is 100 millimeter. So what I'm gonna do, let us work over position vector 3. Position vector 3 is set up between either point A or B. It is set up between A and B. So I don't have point B here. This is the only unknown point actually. So it means that from point A, you're gonna use the comps and draw a curve. This curve is gonna be locus to point B. Make sense? So how long, what is the length of this R3? It should be 100 millimeter, and since you are using scale 1 to 1, so I'm gonna measure 100 millimeter, which it should be 10 centimeters. Then I'm gonna fix with the metal tip at point A that I already have here and draw an arc. This arc, it should be locus to point B. Point B should be located somewhere over this arc. Then do the same. So I've finished, I've done. It is only one step, only one thing that you can do for this position vector. Why? Because its direction is unknown. The same thing for position vector 4. It has also unknown direction. So it is only one thing, and I have to use the comps for the theta 4, for the R4. So the length of R4 is 70. So what I'm gonna do, I'm gonna measure 70 millimeter, which it should be 7 centimeters over the scale. Then from either O4 or B, we have no clue where is point B. So the only point that we have here is point O4. Draw another curve. This other curve, it should be another locus for the point B. So I do have 2 loci, which is this one and this one. So definitely the intersection point, it should be point B. I've located point B. Simply you're gonna connect A to B. This is gonna give us the position vector R3 in this way. Also you're gonna connect O4 to B. This is gonna give us the position vector of R4. So this is gonna be the position vector R3 vector, and this is gonna be the position vector R4 vector, and that's it. For just the position, this is the position polygon. Make sense? But we have to find the unknowns. The unknowns are 2 angles. So here what you're gonna do, you're just gonna do measurements for the angle. How much is theta 3, how much is theta 4, and remember there is no scaling for the angles. So theta 3 should be this angle, as I already defined theta 3 here. It means that from point O, you're gonna draw a horizontal line and start measure till you measure the inclination of this R3. So I'm gonna do the same here. I'm from this point A. Make sure that you have one reference, one of these 2 vertical or horizontal lines or the edges as your reference to completely draw a horizontal line from point A. Then I'm gonna fix at point A to measure the angle of this line. This is the line that I'm seeking, its angle or its inclination to the horizontal axis. So this should be the angle here. The angle, as you can see, it is 10, 15 and 20. It is like 22, right? So the angle, it is this angle. I got it here from the measurement by 22 degrees. So what does it mean? This angle definitely should be theta 3. So theta 3, it will be 22 degrees. And again, if you did the calculation, you're gonna find very close angle. How about theta 4? Theta 4, it should be set up between the horizontal angle and the line, or the R4 itself. So this is the horizontal axis, right? This is the horizontal line. Then from this horizontal line, from point 04, you're gonna fix at the 0 and start to measure the angle. The angle, as you can see, if I remove this one, okay, so this is the line that I'm talking about. This is the line, and as you can see, the line is already located at 10, 20, 30, 40, 50, 65, and it is between 66 and 67. So I'm gonna say that like it is 66.5 degrees. This is gonna give us the theta 4 from the measurement. And by this, we're already done. This data, we're gonna get it from the position polygon. Alright, so this is how we can do position analysis, and these are the 4 cases. Remember that generally these 4 cases, you can replace them with 3 cases of the position vector. The position vector, it will be fully defined, so it is 3 steps. You're gonna measure the angle, draw a light line, then measure the dimension over this line. Then you're gonna mark over or draw the position vector, in case that it is fully defined. In case that the position vector is with unknown magnitude, so you can apply the first 2 steps and stop. Measure the angle, draw a light line, and that's it. In case that the position vector is with unknown direction, you have to use the compass. So you're gonna do it is only 1 step that you can do for this position vector. Just measure the magnitude and fix from any point that belongs to this position vector. Any position vector, it should be set up between 2 points. See which point that you already have in the graph and fix from this point and draw a curve. And that's it for the position vector that is with unknown direction. If you apply these 3 things, or consider these 3 things for the position vector, you can easily do position analysis graphically for any mechanism, whatever it is. Make sense? So this is for the position analysis graphically using the graphical method. The next thing that we're gonna move to is the velocity analysis, but this is gonna be over another video. Alright? So thank you for now, and see you in the next video.